back to part 4. So this is an example of the steps in the reactions and how to calculate K for the third additive step. So if I have a reaction such as this, HF breaking up into hydrogen ions and fluoride ions, and it has a Kc of 2.8 times 10 to the negative fourth, if I were to multiply everything through by 2, giving each component a 2 in front, such as this, a 2, and a 2, then what I do is I take the value that's given for the simplest form of that reaction, 6.8 times 10 to the negative 4, and I square it, raise it to the second power. And then if I were to take this reaction given in this way with this Kc value, and I were to flip it around, reverse the reaction completely in order to take equation 1 and equation 2 to add up to equation 3, when I flip those around, I would take the inverse, as we stated before, of the Kc value for that forward reaction. And those two equations would add up to 2HF C2O4 to the negative second power, 2F negative, and then the H2C2O4, which I got from flipping that one around and changing that. So then what I have is that the value Kc squared times 1 over Kc would give me my answer. So if I take this here, is that 6.8 times 10 to the negative fourth squared. I didn't do that out, but that's where that value comes from, times 1 over 3.8 times 10 to the negative sixth, which is that value there. Then that would equal my K value for that summative reaction number 3. Okay, so that's one nice example of that. So the next thing I'm going to talk about is heterogeneous equilibria. What does that mean? It just means that you have more than one state in your equation. Here I have a solid, here I have aqueous and aqueous. So in this scenario, what I do is I use products the same way I've done it in every other example for showing the Kc expression. But now I eliminate the solid. Solid won't have a concentration, so you won't put it in there. So you eliminate solids and pure liquids from your expression. And so here's another example of it, SnO2, tin oxide, plus 2CO, leading to tin and 2 carbon dioxide gas. So what would I have here? Again, I leave solids out of my expression, and so it would just be the concentration of CO2 squared divided by the concentration of CO squared. So then here, all I have on this page are just a couple more examples on how to calculate K, how to use this expression mathematically. And so let's say I'm given this Haber process again, this equation here, N2 plus 3H2 leading to 2NH3. And let's say I'm given these values at equilibrium. This is very straightforward. I'm given atmospheres of pressure for the hydrogen, for the nitrogen, and for the ammonia. So what this is saying is that at equilibrium, these are the pressure values for these components. So I just plug in those values according to the expression, squared for the NH3, cubed for the H2. I plug in those values and I get a Kp value. It's Kp because I have pressures. And you'll note here that when you use pressures, you use parentheses and not brackets. The common convention for molarity is a value inside of brackets. So anytime you see brackets, it should be molarity. Parentheses indicate pressure. So then there's one more example here. I won't go through it. I'll let you take a look at it yourselves. It's just another example of how to use an ice chart. And the values that would be given for this would be for hydrogen and for the iodine. And then what does that look like here? And so what I know is that I would have to be given a little bit of information, the information in order to get myself to a solution here. This information would have to be given so that I could take and box out this information here to come up with my algebraic expression. 2x is equal to 1.87 times 10 to the negative third. I solve for x, and then I go back here and I'll take my original amount, subtract the x value, and then do the same thing here. Take the original amount, subtract the x value, and then I just take my values, plug them into the expression here, and then I calculate my equilibrium constant, which, by the way, that's a large equilibrium constant. Well, what do we know from that? We know that if it's a large value, that the equilibrium tends to favor the products. There's way more products than there are reactants in the fraction. I'm going to stop there.